Welcome friends to my YouTube channel. Now on my previous lecture I shall discuss about Ehrenfest equation of second order phase transition by using Maxwell's relations, and also I tell about the differences between two specificates, and I discuss it for two different gases, perfect gas and real gas. Okay, now in today's lecture we will do few numericals related to thermodynamic potential. Okay, and this is the last lecture of Maxwell's relations chapter. Okay, so let us do few numericals related to Maxwell's relation. Okay, so first of all, we have to show that minus v square del v of f by v t, this equals to g. Okay, and how we can show it? So let's do. Okay, now this is minus v square and this is del v of f by v t. So what we can write? Minus v square, this we can write 1 by v del f del v temperature constant minus f by v square, and that we simplify. If we simplify it, then we can write minus v del f del v temperature constant plus f, that we can write. Okay, now again the formula of Helmholtz free energy is F equals to U minus Ts, that we all know, where U is the internal energy of a system. So what will be dF? dF will be du minus Tds minus SdT. So this is simply minus PdV minus SdT. Now we have to find out this value of del F del V temperature constant. Del F del V temperature constant, this is simply minus P. So if we substitute this value, then what we get? This is simply P into V plus F. Okay, now F means what? U minus Ts. So what is this? U plus PV minus Ts. This is simply G. Okay, thus we arrive at the result. So we simplify it and write down the formula of Helmholtz free energy, F equal to U minus Ts. So we find dF equal to minus PdV minus SdT. We find out the value of this quantity and substitute in this relation, and we will arrive at the result. Okay, so this is the first numerical. So this equals to RHS, proved. Okay, so fine. Now let us move to the second numerical. Okay, now our second numerical is that we have to show F minus T into del F del T volume constant. This we can write as U. Okay, so F minus del F del T volume constant, this can be written as U. So how we can show it? So given that left hand side, this equals to F minus T del F del T volume constant. Okay, now we all know the formula of F, that is simply U minus Ts. Okay, so what will be dF? Again dF equal to du minus Tds minus SdT. So what is du minus Tds? Minus PdV minus SdT. So what will be my del F del T volume constant? This is simply minus S. Okay, del F del T volume constant, this is equal to minus S. So if we substitute this value here, so it becomes F plus St. And what is F plus St? That is simply U. So we arrive at the result. So this is also a small numerical problem. Okay, this is also a small numerical problem. Okay, so we arrive at the result. So let's move to third numerical. Okay, the third numerical is that we have to show that minus T into del 2G del T2 pressure constant, this equals to Cp. Okay, Cp equals to minus T into del 2G del T2 pressure constant. So let us proceed. So what is LHS? Minus T into del 2G del T2 pressure constant. Now what is G? We all know U plus PV minus TS. So what is dG? That is simply du plus pdv plus vdp minus tds minus sdt, and du plus pdv means dq, that means tds. So these cancels, so it becomes vdp minus sdt. So what will be del g del t pressure constant, that is minus s, and what is del 2g del t2 pressure constant? This is simply minus del S del T pressure constant. Okay. So if we substitute this value, so what we get? This is minus T, and this is what del 2G del T2, that means minus del S del T. So plus del S del T pressure constant. So T del S means del Q. So what is this? Del Q del T pressure constant means Cp. Okay. So this is also a easy numerical. So you have to understand what you are going to find out. Just see the LHS or RHS given and try to find out this quantity by using the relation which is involved in this term, because here G is involved in this relation. So you have to write down the formula of G and then proceed. So this is another numerical I have done. So let us move to another numerical, that is number 4. You have to find out minus t square. Dear guys, just take your pen and paper and try and note down these problems. Okay. Minus t square del del t of f by t into v. This equals to u. Okay. So what is given in the left hand side? This is given minus t square del del t f by t volume constant. Okay, this is given minus t square into del del t of f by t volume constant. So what you can write? Minus t square, this is simply 1 upon t del f del t volume constant minus f by t square. Okay, this minus t square into 1 by t del f del t volume constant minus f by t square. Now what you can write? F equal to u minus ts. Okay, what you can write? F this equals to u minus ts. Okay, so just simplify this. Df this equals to du minus tds minus sdt. So what is this? Du minus tds minus pdv minus sdt. So what is del f del t volume constant? This is simply minus s. So this is simply, you can write minus t square, and this term is minus s, so minus s by t plus f by t square. So what is this? Minus plus st. Okay. Oh, sorry. there is a minus sign there, so this is plus f. Now from which, what is st plus f? F plus st means u, so we arrive at the result. Okay, so this is RHS and proved. Okay, so this is our fourth numerical. Now here f is involved in this relation, so write down the formula of f and find out according to this relation. Okay, so this is the another numerical of today. Now we have to, our next problem is to find out the Joule-Thomson coefficient by using Maxwell's relation. We will learn the Joule-Thomson process in low temperature physics chapter next, but now we are going to find out the Joule-Thomson coefficient. You will know that Joule-Thomson coefficient is a change in temperature to the change in pressure at constant enthalpy. This is known as the Joule-Thomson coefficient. In change in temperature to the corresponding change in pressure at constant enthalpy, we have to find out this expression, and we have to show that this expression can be written in this way: 1 upon C T into del V del T pressure constant minus V, right? Sorry, V. So we have to show this expression, okay, by using Maxwell's relation. Now we have to start from the definition of enthalpy, because here enthalpy remains constant, that we have to put. So we know that the enthalpy of a system can be written in this way: H equals to U plus PV. U is the internal energy of the system and PV is the work done. So what is dH? This is simply du plus PdV plus VdP. And what is this? TdS, okay, plus VdP. Now in JT process, enthalpy remains constant, that means change in enthalpy dH is 0. So if we substitute this, we become this TdS plus VdP, this equals to 0. Okay, just give it a name 1. TdS plus VdP, this equals to 0. Now assume that entropy as a function of pressure and temperature. Assume entropy as a function of pressure and temperature to find ds. So what will be ds? Since it is a perfect differential, ds will be this: del S del P temperature constant, del S del T pressure constant into dt. Okay, so this will be my ds. Now we have to substitute this value of ds in equation 1 and see what we are getting. So put the value of ds in equation 1. Okay, so if we put the value of equation of ds, so what we get, I also erase it. So tds, that means what is ds? We find it del S del P temperature constant dP plus del S del T pressure constant dt plus V dP, this equals to 0. Okay, now from Maxwell's relation, what we can write: del S del P temperature constant means minus del V del T pressure constant, minus del V del T pressure constant. Okay, minus del V del T minus del V del T pressure constant plus, this is what T del S means, del Q del T pressure constant means Cp dt. Okay, plus V dP, this equals to 0, minus T into del V del T pressure constant dP plus Cp dt plus V dP equal to 0. So what we get? We get Cp dt, this equals to T del V del T pressure constant minus V into dP. Cp dt, this equals to this. So from which what we get? dt dP, we get 1 upon Cp T into del V del T pressure constant minus V. And now what is this? Change in temperature to the ratio of change in temperature to the corresponding change in pressure is a measure of Joule Thomson coefficient. So we arrive at the exactly similar expression that I require. Okay, so T into del V del T pressure constant minus V. Okay, dear guys, with this Maxwell's relation chapter is finished. Now in my next lecture I will going to start the 5th chapter of thermodynamics, that is Joule Thomson porous plug experiment, or you can say low temperature physics. Okay, so if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay, thank you.